Hello, JE Chams. Welcome to this particular session wherein today we'll be talking about one of the skull crusher problem for atomic structure. Hope you like the problem and understand it well. The question is, the wave function xi NLM is a mathematical function whose value depends upon the spherical polar coordinates r, theta and phi of the electron and characterized by the quantum number NL and M. Here r is the distance from the nucleus, theta is co-altitude and phi is azimuth. In the mathematical functions given in the table, Z is the atomic number and A0 is the Bohr radius. Okay, we have been given with the three columns, column 1, 2 and 3, and basically our agenda is to actually match them properly, and then we'll be moving ahead with the questionnaire sessions. There are three questions for this particular question. I mean to say there are three sub questions for the question given to us. The very first question is asking us for He positive ion, the only incorrect combination is. Second question is for the given orbital in column 1, the only correct combination for any hydrogen-like species is. And the third question is for hydrogen atom, the only correct combination is. So we'll be dealing with these three questions later on, but first of all, let me actually talk you regarding the Schrödinger wave equation. Now this Schrödinger wave equation can be solved for hydrogen-like species more easily in the spherical coordinates r, theta and phi. Now when Schrödinger wave equation is solved for hydrogen-like species, the obtained value of xi, this is the wave function I'm talking about, xi, it could be factorized into only, I'll just say it could be factorized into one containing only r and the other containing theta and phi. That means xi is equals to xi r, okay, multiplied by xi theta comma phi, wherein this xi r is known to be as radial part of the wave function, and the xi theta comma phi is known to be as angular part of the wave function, okay. This xi r, ये हमें क्या बताता है? न्यूक्लियस से डिस्टेंस चेंज करो तब ये xi r बदलता है, और ये हमको किसकी वैल्यू देता है? एजीमुथल क्वांटम नंबर, okay, I'll just say principal quantum number and azimuthal quantum number. Angular part of the wave function, it actually tells us about the azimuthal quantum number and magnetic quantum number. This xi basically it corresponds to the atomic orbital, and it is characterized by a set of quantum numbers n, l, m, and one is more to be recognized afterwards, which is spin quantum number. Schrödinger wave equation tells us about the three variables, three quantum numbers n, l and m. That's the main thing you need to remember for this particular question just for now. I'm not going into depth. I'm just telling you what you should know before you solve this particular question. Fine, that's absolutely right. Yes. Now if I just talk about the columns over here. First of all, let's actually see which particular part is right and which particular part is wrong. Before I just deal in anything, let me actually talk about a Schrödinger equation, a normal Schrödinger equation. Okay, so if I just talk about one particular thing, xi, the wave function n, l, m. Okay, I just told you, it is having two parts, radial part and the angular part basically. Okay, totally agree. So we can write it like this, r, okay, n, l of the r, then theta of the theta and phi of the phi. Kind of like this. I can represent it like this. That's absolutely right and cool. Okay, ma'am. Now if I just talk about the value of r, n, l, okay, it's been derived and so on. I just know the value. It's represented as k dot e raised to power minus sigma by 2 dot sigma raised to power l. Now this sigma is basically equals to twice of zr upon na0. This is rnl, the radial part of the wave function, how we actually represent it. Supposingly, if I just take a random Schrödinger equation, xi is equals to 1 upon root 3, okay, zr upon 2a0 raised to power 3 by 2. ZR upon A naught raised to power ZR upon A naught E raised to power ZR upon 4A naught. Okay. Then I take sine square theta. Okay. E raised to power plus minus M phi. Fine? Clear? Okay, that's absolutely right. Now let me tell you one thing. This is a normal random Schrodinger equation I've taken and it's supposedly given to you. Now from this Schrodinger equation, we can find out the values of n, l and m basically. How come? This particular integer, over here I have written 4a naught, it could have been written na naught, fine. So basically it is going to give us the value of n. It is going to give us the value of n basically. Okay. If I just talk about the value of L, we are supposed to get the value of L from here. Value of L. Value of L from this particular function. It could be sine or it could be cos. Fine. And e raised to power plus minus m phi, it gives us the value of magnetic quantum number. Value of magnetic quantum number. Value of m basically we are supposed to get from here. Fine. So from the Schrodinger equation, we are supposed to get the three values, three quantum number values: principal quantum number, azimuthal quantum number and magnetic quantum number. Clear? So the value of n over here, if I just talk about, it has been given as 4. The value of L is 2 basically. Supposingly, if I just say that nothing has given over here, supposingly, if I just say it could have been plus minus theta. So the coefficient of this theta gives us the value of m, and over here the value of m is 1. That's absolutely right. So which particular wave function it corresponds to? 4D basically. This is what we actually get from a Schrodinger big equation. Fine. I actually probably hope that you have understood what I want to make you understand. Fine. Well, let's talk about the very first column, 1s orbital. We are talking about 1s orbital matching with xi n l m directly proportional to z upon a naught raised to power 3 by 2 e raised to power zr upon a naught. So over here, if I just talk about for 1s orbital, what is the value of n we are supposed to get from here? It is n equals to 1. The coefficient of a naught I'm actually talking about. Fine, that's absolutely right. Now what else? So for 1s orbital, fine, the value of n is equals to 1. Absolutely right. Since over here we haven't given with the angular part, so we can consider the value of L and m equals to 0. Okay. So over here I can just say 1, it matches with I. 1 matches with 1. That's absolutely right. Okay, ma'am, 1 matches with the 1. What else we are supposed to talk about over here? If I talk about 2p z orbital, 2p z orbital, so it's z upon a naught raised to power 5 by 2 r e raised to power z upon e raised to power minus z r upon 2a naught cos theta. Cos theta will be over here, not over here. There is some error. Okay. So if cos theta is there, that means the value of L is equals to 1. Cos raised to power 1 and theta. So value of L is equals to 1. Okay. What is the value of N? It's 2a naught. So value of N over here is equals to 2. Okay. There is nothing given for the value of M. So the value of M is equals to 0. So n is equals to 2 and L equals to 1. So it becomes 2p. So third connects with the third. Yes, I can just say third connects with the third. It's absolutely right over here. Done? Okay, done. Now what else we are actually left with? One more thing. You can just see a graph over here. Yes, ma'am. Can you just see a node over here? I made you explain in my session class that this is a graph between the wave function and r upon a naught, and see this particular graph is cutting this particular axis. So this is kind of a node we are actually supposed to find out over here. That's absolutely right. Yes, absolutely right. So what we can actually do over here, what we can actually go ahead with over here. Wait a minute. It's 2s orbital. We do have 2s orbital. Do 2s orbital have one radial node? What's the formula of radial node? It's equals to n minus L minus 1. What is n over here 2? What is S0? Minus 1 equals to 1. So second connects with second. And over here we can just see that this particular graph is cutting only at one point. That means this is the node. This is the node where the probability of finding the electron is 0. So I can just say one thing, that second connects with second and it connects with the very first graph. I think it's P basically, yeah. So it connects with P. Second, and P. Absolutely right. It connects, the dots I'm connecting with each and every point over here. Let's talk about dz square orbital now. They are saying xy plane is a nodal plane. XY plane is a nodal plane for PZ orbital. XY, if I just talk about PZ, okay, suppose I'm talking about PZ. This is PZ I'm talking about. This is the Z axis, this is the X axis, and this is the Y axis. So for PZ orbital, we do have the nodal plane XY. Okay, angular node I'm talking about. When we talk about angular node, we talk about flat planes and the cones basically. So we do have XY plane to be a nodal plane where the probability of finding the electron density is 0 for PZ orbital. For PZ, okay. If I just talk about dz square, if I just talk about for z square, for dz square we do have kind of like this basically. And over here, I'll just say there is no XY plane to be a nodal plane. Rather, there are the cones. These are the cones, so spherical cones, then wherein the probability of finding the electron density is 0. I'm talking about the cones. So fourth do not matches with the fourth basically. Fourth do not matches with the fourth. Okay, yes, that's absolutely right. Okay. So what else we are over here with? See, one thing is for sure, second, and P. 1, 1. And if I just talk about, if I just go with the other column over here, probability density at nucleus is directly proportional to 1 upon A naught cube. 1 upon A naught cube I'm talking about. Okay, ma'am. So what else we actually want over here? See, for 1s orbital, 1 is matching up. Xi square, probability density at nucleus. Probability density as at nucleus. So for s orbital, if I talk about probability density, if I just talk about, let me square it up. If I just square it up, if I just square this particular thing up, so xi square, if I'm squaring it up, it is directly proportional to, it will be then directly proportional to z 3 by 2 whole square upon A naught 3 by 2 whole square. So it comes out to be z cube upon A naught cube. So over here z square is inversely proportional to A naught cube. So yes, 1, 1 and q, it can actually match. 1, 1 and q, yes. Probability density at nucleus is absolutely right. It matches with this also. Talking about probability density is maximum at nucleus. See, for the s orbital, probability density is maximum at nucleus. क्लियर. फॉर पी एंड डी ऑर्बिटल्स वहां क्या होते हैं, इलेक्ट्रॉन को पाने की जो संभावना होती है वो 0 होती है at the nucleus, but for the s orbital, since it is close to the nucleus, so वहां पर इलेक्ट्रॉन को पाने की संभावना ज्यादा होती है. So we can actually go for a thing कि हमारा q भी सही है, हमारा r भी सही है. For if I just talk about 1 1 q, and also you can just say for 1 1 r, for 2s orbital also you can just go with this particular thing. Fine, yes. So P is actually, we have matched with Q, we have matched with R, we have matched with. Now what are we left with? The S particular part. Energy needed to excite electron from n equals to 2 state to n equals to 4 state is 27 upon 32 times the energy needed to excite electron from n equals to 2 to n equals to 6 state. Okay. इसके लिए भी we'll be actually calculating the things out. So just have a look. This is the last part we are actually going to do probably. So they are saying 27 by 32 is equals to E4 minus E2 upon E6 minus E2 basically. And we know the formula for it. which probably know the formula for it, and that's absolutely 13.6 1 upon n1 square 1 upon 4 minus 1 upon n2 square divided by 13.6 1 upon n1 square minus 1 upon n2 square. When you solve this whole expression, you are supposed to get the answer to come out as 27 by 32. So we'll say this is also right. This is also right, basically. That's absolutely right. That's absolutely right. Now let's come to the question part. Now they are saying for helium He positive ion. So He positive ion, it belongs to hydrogen-like species. It belongs to hydrogen-like species. Yes. We want to talk about the only incorrect combination. Incorrect combination we need to talk about. Okay. So it's 1, 1, S. If I just talk about for 1, 1 and S. So 1 and 1 matches with 1, and it also matches with S because we are talking about hydrogen atom. So 1, 1, S is absolutely right. Talking about second Q, if I just talk about second, I have just said second P. Okay, but if I just talk about for second and Q, it is for 2s orbital. Yes, for the s orbital we do have a function, this one only, and for it it's directly proportional to 1 upon a naught cube. So second Q is also right. This is also true. This is true. This is true. Talking about 1/3 and R, 1/3 and R. Okay, this is 1. Okay, matching with the third. Not at all. How this one matches with the third? No, it doesn't matches with the third. So we want only incorrect combination. This is incorrect combination. This is incorrect combination. Right answer for the question. And they are saying 1, 1 and R. Let's see 1, 1 and R. So this is 1 matches with the 1 matches with the R. Probability density is maximum at nucleus for the s orbital. Absolutely right. This is also true. So the right answer, only incorrect combination, is option number C. Hope that's absolutely clear. Okay. Talking about the second particular point, for the given orbital in column 1, okay, the only correct combination for any hydrogen-like species will be what? Okay. So for this, let me actually have a look. It's second and P. They are saying for column number 1, let me actually check it again. For column number 1, only correct combination. Second P. Yes, second and P. I marked it over here. Second and P. You can just have a look. Second matches with the second and it matches with the P. Absolutely right. This is the correct combination we do have. Second and P. If I just talk about 1, 2 and S. 1, 2 and S. Let me check. 1, 2. How 1s orbital is going to have one radial node? 1s orbital will not be having a 1 radial node, 0 radial node. So it's absolutely wrong. And the rest also you can match it up because I have actually shown you each and everything. So these 3 are wrong. This is the only correct combination that we are having into our pocket. Let's move ahead and talk about the last question. For hydrogen atom, the only correct combination is hydrogen atom के लिए correct combination चाहिए हमें. Okay, so 1, 1. And let me actually talk about for hydrogen atom correct combination. So we have 1, 1 S, we have 1, 1 Q, we have 1, 1 R. So let me actually check the particular thing. We have 1, 1 S. Yes, this is the correct combination. 1, 1 and P. P is the graph and the graph is not for 1s orbital. Totally wrong. 1/4 and R. Let me check 1/4 and R again. 1 and 4th. 1s orbital will have XY nodal plane? No nodal planes. No, not at all. Not at all, dear one. Not at all. So this is also wrong. 2, 1 and Q. 2, 1 and Q. This is 2 matching with the 1 and matching it. If I just talk about 2, 1 and Q. Okay, let me check it out. So, yes, if I just talk about 2, 1 and Q. They are saying, okay, so it's second. Then 1 and the Q. We need only in one correct combination. So it also do not matches with us. It's only option number D, 1, 1 and S. 1, 1 and S. 1 matches with the 1 over here and it matches with the S. Okay, that's absolutely fine. Yeah, that's absolutely fine. See what actually I want to say, 2 does not match with 1. Why? Because over here what we are having, the value of n is equals to 2. the value of n is equals to 2, and over here the value of n is equals to 1. That's the main thing. So it does not match us. But yes, if we talk about xi square, if we talk about the probability density, we'll be actually dealing till here. So this will be actually appropriately, right? So yes, I'll just mark only one particular thing, that this 1, 1 and s is the appropriate correct combination for hydrogen-like atom. Hope all the three parts have been clear to you. So for this particular question, if you want to solve it in a proper way, in a right manner, you need to know each and everything about the Schrodinger wave equation. This question came in JEE Advanced 2017. Hope you have liked the solution, you have understood each and everything. Thank you so much.